When you see one of those giant wind turbines turning on a hillside, it's pretty impressive. They're just these incredible feats of engineering. But they've got a fascinating little secret, a real puzzle at the very core of their design. So let's just jump right in with a question that seems super simple, but the answer is surprisingly cool. Why can't we capture every single bit of energy from the wind? Why isn't a wind turbine, perfect? Well, the answer isn't about shoddy engineering or anything like that. Nope. It's actually all about the fundamental physics of how stuff moves. It's a little weird and counterintuitive, so let's break it down. The whole idea boils down to something called Betz's law. It was published way back in 1919, and it basically puts a hard ceiling on wind power, no matter how clever our designs get. And it all starts with a simple thought experiment. Okay, so just picture the perfect turbine, right? A machine that's so good it pulls every last drop of kinetic energy out of the air that passes through its blades. So what happens to that air once you've taken all its energy away? Well, it would literally just stop moving. The air coming out the back of the turbine would have a velocity of 0. And that is the big problem. If the air stops, you get a traffic jam. A wall of still air piles up right behind the turbine, and no new wind can get through to spin the blades. The turbine basically chokes itself off. So a perfectly efficient turbine would stop working almost immediately. Okay, so if 100% is impossible, and 0% is useless, there's got to be a sweet spot in the middle. And believe it or not, physics gives us a very, very specific number for that sweet spot. And there it is, 59.3%. That is the absolute theoretical maximum amount of energy a turbine can ever capture from the wind. We call it the Betz limit. What's so important about this number is that it's the perfect compromise. See, to keep the air moving through the turbine, you have to let some of that energy go. So 59.3% is that ideal balance point, where you're grabbing the most power you possibly can without causing that big aerodynamic traffic jam. And this is where it gets really interesting. When you look at the real world, you've got the dream of 100%, then you've got the hard physical limit, 59.3%. And then you have our best modern turbines. They actually operate at around 45 to 50% efficiency. Now, that might not sound amazing, but it's about 75 to 85% of the Betz limit. We're getting incredibly close to the theoretical maximum. Here's a cool little piece of history for you. We call it Betz's law, but he wasn't the only one who figured this out. A British scientist named Frederick Lanchester and a Russian aerodynamicist, Nikolai Zhukovsky, both independently came to the exact same conclusion at almost the exact same time. It's just a great example of a fundamental truth that was just sort of out there, waiting to be discovered. Okay, so that's the beautiful, clean physics of it all. But what happens when that elegant theory slams into the messy, complicated world of real-world engineering? Let's take a look. We can actually get a fantastic peek behind the curtain from this report by the National Renewable Energy Laboratory, or NREL. Back in '99, they were designing a new blade for one of their test turbines. And their goal wasn't just to make power, it was also to get really high-quality scientific data. And right here, you can see the huge gap between theory and reality. Betz's law comes from this perfect, idealized model, an actuator disc that's paper-thin and has no friction. The NRL team, on the other hand, had to build a real thing. It had to have a complex shape, it needed to hold instruments, and it even had to be compatible with their older experiments. I mean, just look at these constraints. They couldn't make the blade as thin as they wanted because they needed a certain width just to install their pressure measuring instruments. They even had to lock in a specific width at one point on the blade just so they could compare the new data with old data. Every single one of these decisions is a trade-off between pure aerodynamic perfection and the practical needs of science. This just goes to show how much these designs have to adapt to the real world. They made a baseline blade for a 3-bladed setup, but then they also had to design a longer version for a 2-bladed turbine. So you see, engineering isn't about finding that one single perfect answer. It's about finding the best answer for a very specific set of problems. So we've got this hard limit, 59.3%, and we see how engineers have to work within it. But what if I told you that the limit, well, maybe isn't quite as absolute as it seems? Yeah, it turns out when you dig into it, Betz himself never claimed his law was this totally unbreakable, unconditional rule for any possible wind-catching machine you could dream up. See, the law comes with some very specific assumptions, and wherever you find assumptions, sometimes you can find loopholes.
Here's the key. The entire idea behind Betz's law is based on a single, isolated rotor. But what happens if you start lining them up? What if you use more than one?
Think about it this way. A turbine that's working at the Betz limit still has to let air pass through it, right? Well, that air, the wake, it's slower, but it still has kinetic energy. So in theory, you could put a second turbine downstream to capture some of that leftover energy. A combined multi-rotor system isn't playing by the same rules as a single rotor, and theoretically, it could actually push past that 59.3% barrier. And this all leads us to a final, really fascinating question. While we're getting closer and closer to the limit with our single rotor designs, could the next huge leap in wind energy come from something totally different? Maybe from complex, multi-stage turbines that work together to finally and officially break the Betz barrier. It's a puzzle that engineers are still trying to figure out.